Yeah, so good afternoon to all. This is CMOS analog IC design E5 and we are going to start with the new chapter called single stage amplifier. Today is September 12, 2023, and this is lecture number 8. So, what is the role of a transistor? Okay, before going to that, let's revise what we did. Right, so we studied 4 things. Right, the 4 silver bullets. Can you someone tell me what were those? Transistor is in triode region or in linear region. It will exhibit the resistance called R1, which is nothing but del ID by del VDS, where ID equation will be 1 mu1 Cox W by L, VGS minus VTH, VDS minus VDS. Hmm? R1 will be 1 of yeah. Then next was when it's in saturation, you can find out GM, which is del ID by del VGS, and it's following the equation of square law. Right. You might have channel and modulation also. So R1 is nothing but RDS or R0 are going to be 1 by lambda ID. Right? You can find out that with the additional equation of 1 plus lambda VDS. So 1 plus lambda VDS, and last one is the body effect. There is some problem with body effect. You will experience some extra GMBS. There is no problem, right? Okay. If anything is running, I will close it. Still it is slow. Okay, so with the body effect, GMBS will be observed, and GMBS is nothing but eta times GM, right? So eta is some number, 1, 2, 3, 4, depending on your particular process. So in that case, 1 by GM is actually the smallest one, and 1 by GM is BS is second smallest one, and then this by GM. Right. So this is the relation. These are generally in ohms. This is in kilo ohm. That's how it becomes high impedance category, and this goes in regime of low impedance category. Right. So this is what we studied, right, in the previous device understanding thing. Along with that, uh, tomorrow is the laboratory, right? So you can check the CV curve for different MOS caps, which I gave it to you, all 4 MOS caps. Okay, so now let's go to the real thing, which is the chapter where our main goal is to use transistor as an amplifier. So its role is to amplify. Its role is also to act as a switch. However, we are not talking about that. We are considering ourselves into the amplifying region, where you are working with the small signal AC input. We are amplifying small signal AC input, which is at low frequency. However, not at DC. It might be 0, but not at DC. It might be some other value, but very low, where capacitances are not available. When the capacitance will be there, then that will be the high frequency small signal AC model, which will be different than what we have studied. Just for your information and your reference, I am keeping this model. So this is the actual model, including the channel and modulation as well as body effect, right? So this is how it will look like, right? So in that case, this is low frequency, still not at 0, not at DC, low frequency small signal AC model. Right? This is what this model is. High frequency will have capacitance. We'll study that maybe in later on. Different chapters will be there, right? Now, and we are interested in the gain at AC only, little bit higher than 0 frequency, right? And we are interested in the small signal gain. Understand what is small signal? We understand that, right? So depending on the gain of the amplifier, accordingly you can define the input as small signal or maybe large signal. Now let's go to here. We know about this one very, already we discussed that. This is a revising same thing. So if I am keeping my transistor like this configuration, where input I am applying from here and output is here. Note that what I am telling now is actually a trick to solve complex networks. So through equations also you can follow, which is also simpler one. However, with as time progresses, you will realize that trick might be useful, or if you know the impedances at particular places, that makes the faster system and faster output, and analysis will be easier for you. So in that case, what we are saying is there are two two impedances. I call it Z in and Z out. But note that even though input we are connecting here, I am saying this one is input impedance, just for my for my technique. This is a technique, understand? So I am calling input impedance over here with the fact that if you are looking into this, it's infinity. There is no, right? And why I am doing this? Just to make sure that this current and this current, both side, for a given input current, or the current which is here and current which is going from here, both have to be equal, right? So if I say that Z out times ID divided by Z in times IS, can I call that one as gain? Right? By the way, ID is equal to IS. That's true for MOSFET. However, in a case of BJT, you have to add beta IB, and then accordingly you have to go with that, and it will be beta Z out by Z in that case. So here the gain is Z out by Z in with the indicated place where we are seeing the Z in. Right? Most of the time here, looking from here, it's 1 by GM, so it's different thing. But anyway, so what we are seeing over here is ID equal to IS, IG equal to 0, and small signal AC gain is nothing but Z out by Z in, where I am seeing Z in from here. You can call this one, if you don't like this terminology, then you can call this gain as nothing but ZD by Z source also. Okay, both are same way. Okay. Looking into the system in source terminal or in drain terminal. So if I'm interested in finding out the impedance in source terminal, what is the impedance? 1 by GM in shunt with RO. You can approximate this to 1 by GM if you wish, right? Other thing, looking from drain side, what is the output impedance? Only R0, right? There is no GM because already this is VGS, so gate and drain both are shorted. So we are following the same Thevenin theorem. So these two are the things, that's fine. However, when we are looking into this, if you looking into source side, where as I'm saying, this is a trick or the technique to achieve the gain and other things properly. So when you are looking into this, actually you are applying the known Thevenin voltage here, and you are trying to measure the threshold Thevenin current going inside. So VTH by ITH is going to give you the current, or VTH by ITH is going to give you ZL. However, it's in opposite direction of this one. Look at this. So whenever you are looking from the source side, the current is experiencing the opposite direction. Then you have to keep the minus sign just for this one. There is no minus impedance. However, because of the current which is in a different direction, then you can write down Z out is nothing but R0 divided by 1 by GM. So that will give you minus GM times RO, right? So that's one thing. Or maybe some books, they do not like this one. They might be like writing R0 divided by 1 by GM in shunt with R0. It's also correct. Okay. So whichever way you like, you can keep it over here. By the way, this was a single transistor. This was a single transistor. And single transistor gain, just now we found out when we are keeping it with this as input and this as output. In other terminal as 0. If you are doing this and if you are finding out its gain, it is going minus GM times RO, right? Everybody agrees on that. Where GM is transconductance, RO is nothing but a channel and modulation resistance. This particular gain, we are not going to call it as gain of one transistor. There is some specific name. The name is intrinsic gain of the amplifier or single transistor. Gain of a single transistor. Right. So that's the technical terminology. You can see the intrinsic gain for a smallest value of W by L in model parameter as well. If you want to check the intrinsic gain, that will also be written in model parameter. Generally, this is between 18 to 20 volt per volt, right? So 18, 20 is how much in dB? 26 dB, right? So 20 dB is 10 volt per volt, double is 6 dB, so 26 dB, right? So around 26 dB you can achieve. This is tentatively depending on the technology node which I am talking about, is around 90 nanometer or something, right? This is true for above that. As you are going lower, maybe 3 nanometer, maybe gain might be like 5, 6 only. It depends. In 180 nanometer, maybe the gain might be much higher, so you can achieve more gain very easily over there. Bigger technology node has a problem of the achieving very high frequency, and this term FT of the device, right? So we'll find out how much is FT you can go when we are going to study the high frequency model. Right now we are studying on low frequency, so low frequency wise the intrinsic gain is minus GM times RO. So this is frequency with respect to the magnitude of a single transistor. This is known as intrinsic gain. This is going to be known as transit frequency, which already we talked about. I'm keeping it just for revising what we studied, right? No problem, right? Okay. So anyone who does not, everybody are able to see this whenever this transistor is there. Can you replace this in your mind? Are you able to see, right? Input side there is infinite, output side GM VGS and in shunt with R0, right? You have to see this. Okay, so if this is the case, let's say, if I'm changing the configuration a bit like this, so replace in back of your mind the small signal model where input is infinite, output side GM VGS and R0 in shunt. If you are in this configuration, if you are replacing this, if you are looking from here, what are you going to see? 1 by GM in shunt with RO, right? Okay, and you can approximate that to 1 by GM, no problem. If you are looking from here, what are you going to see? Why 1 by GM? Okay, 1 by GM in shunt with R0. True. What about this one? Of course, same, right? It's shorted. You can approximate every side as 1 by GM. Understand, when you are doing this, any of the side you are saying it's a low impedance, right? We are saying only low impedance. Why it is low impedance? Because 1 by GM is in ohms, right? Maybe 100, 200 ohms. So any side you are seeing in this particular configuration, this particular thing is diode connected transistor or diode configuration based transistor. From whichever side you want to see, it's going to show you low impedance only. And if you are keeping this at the output side, it will make the circuit as current, right? If you remember, output impedance is low, means it's current source, right? So let's go a little bit further. If there is a circuit like this where I'm connecting here something called DC bias. So every one of you know what is bias, DC bias. What is DC bias? Yeah. Green t-shirt.
So DC voltage.
But already written DC. Bias is equal to voltage or what? What is the role of bias?
Sir, to drive MOSFET in, so that we can amplify it in saturation region. So, with
You
DC,
want to say that bias is the one?
Sir,
Where
with DC we can get the operating point where we can superimpose small signals so that it can be in that amplifying region.
So what is bias?
So bias is a driving DC voltage.
Bias is a voltage. It might be AC or DC. I wrote it. Okay, let's write it this way. Bias might be AC also, DC also. It is not compulsion. If it is small, like small thing, then it's okay, fine. It might be DC, it might be AC. But bias is the potential which makes sure that the transistor is in particular region, right? Either in saturation, cutoff, accumulation, wherever you want to keep. This bias voltage will decide that. So if I am applying like this, understand? I applied the large signal thing like this. I can apply, right? Nobody can stop me. But as the time progresses, look at this, all these points. They are acting as a bias potential, right? And maybe with the big variation going from 0 to maybe VDD. It is going and I am applying here. That is also okay. We can apply it. Nobody is stopping that. But bias is the potential which is going to make sure that your transistor is in particular region of operation. I am writing this with DC just to make sure that whatever bias I am giving, it's DC bias. Okay. Generally bias is DC. However, it's not compulsory that it has to be only and only DC. AC can also bias the signal, the circuit, right, with the available voltage. Okay. So I applied here DC bias. Now I'm seeing the impedances from different places. So please tell me, what are you going to see if you are having the this configuration? Source side, what are you going to see? 1 by GM, in shunt with RC. Okay, you can call it 1 by GM, no problem. What about this one? Looking from drain side.
Same.
Hmm?
Same 1 by GM.
Why 1 by GM? Why 1 by GM?
Gate to source. R0.
R not, right? Understand, when we are doing this, one important thing we have to remember during small signal AC analysis. Understand, small signal AC analysis, I am keeping this in different colors so that you can remember it forever. That small signal AC analysis is about AC. Wherever you are seeing DC, it goes to 0, right? AC is equal to, if it is DC, if I am saying I am applying DC, it's equal to 0 volt AC plus some DC voltage, right? That is the meaning of that. So when you are doing this small signal AC analysis, understand wherever you are seeing DC potential, actually it's equal to 0. In your small signal model, it has to be grounded. Okay, this is again a technique. Okay, in books also they are following, but this is a technique. You have to see that even though it's a DC bias, so DC bias is not going anywhere. It is there, but for the AC signal or AC analysis, wherever AC signals are there, those will be actually activated at that time. Rest of the things will not be there. Okay, so if I am applying somewhere, okay, maybe another circuit is there, like this. So now tell me, if I am looking from here, what will the from drain side? Look at this. This is a drain. Anode. Okay, or RDS, whichever you like. Looking from source, 1 by GM. Right. You can also see from gate also, it's always infinite. By the way, note that this VB in throughout the book, it's actually B stands for bias. Okay. And generally, it's taken as DC at a time, so you should consider that potential as DC bias voltage, and it has to be grounded during the AC analysis, small signal AC. However, when we are going to do the common mode analysis, at that time this DC will be activated where AC goes to 0. We'll study that, but yeah, this is how it goes, right? No problem, right? Looking into impedances, okay, no problem. Okay, so let's summarizing what actually we have seen. So every NMOS or PMOS, so those things which have we made for NMOS or PMOS, like it's also applicable for both the transistors. Small signal AC, okay, small signal AC will contribute impedance of minus 1 by GM at the source terminal. So whichever configuration you like, you just make it. Always it gives minus 1 by GM. I am adding this with the fact that if you are doing this one, input has to be here. And looking from here, so of course minus will come. So you have to take care of it. So actually I cannot write this one. It's only 1 by GM. The current flow has to be incorporated in the final equation. One more thing, if you are looking from the drain terminal, you observe that it's approximately R0. Right? One more thing, every diode connected NMOS or PMOS transistor will contribute minus 1 by GM at actually any terminal. Looking into any terminal, it's 1 by GM. Right? Or you can say that drain terminal is always going to give you high impedance. Source terminal is, okay, in diode it's always low. Here it's always source is low, and every NMOS PMOS transistor made current source. Okay, so this particular configuration is known as the current configuration. We will study that right now. Just maybe keep it in your mind that it's current configuration. It provides the required current. We'll study that when we are going to study the current mirror, because this DC bias voltage is actually generated from some other circuit. You must have studied somewhere, right? Current mirror. So it's a current mirror. Actual circuit is like this. Actual circuit is like this, and DC bias voltage is actually generated from here, which is DC by nature, and this is going to give you the required bias. So this particular configuration is known as the current configuration. So in current configuration, looking from drain is going to give you R0. So that is what written here. right? So current source is going to give you R0, which is actually high, and that is what expected from any current, current source, right? Okay, so now let's go with this one. First of all, common source amplifier, which is you know the first configuration with the known facts which we have actually seen. So we can have three different possibilities of the load. Till now, whatever we have learned, it does not have any load. I just kept one transistor. I have not applied VDD anywhere. I have not kept any load, right? So when I'm going to apply that, what will be the gain of that circuit? That's what we are going to find out, right? So let's assume that this is the circuit. Okay, again copied from Behzad Razavi, right? So if this is M1 and this is RD, if you remember my trick, first of all, why this is common source, by the way? What about this one? Which amplifier is? How do you know that its gate is common? Let them speak. Yes, let them speak. Tell me.
Which is at low voltage.
Hmm?
The terminal which is at low voltage.
Which one is low voltage?
This B bias.
Why? It is some DC potential you have applied, right? You applied some voltage, right?
DC part will be zero.
DC part will be zero. Okay. So you are right. You are also right. Okay. So here we have to see the lowest potential. Like with respect to which everything is being measured. But note that here one more extra thing has to be there. Lowest AC potential. Okay, not other potential, lowest AC potential, or we need to see the AC ground. Where is the AC ground? So here in this case, this is the only place where there is an AC ground. We know that B bias is an AC ground. So this is an AC ground. Other place, here we are applying some potential, right? Some AC input is here, and from here you are taking the output. So this is AC output, and maybe next one. Look at this. If you apply here V in, so this is AC input, this is AC output, and this VDD is equal to AC ground, right? Even though it's the highest potential we are applying to the circuit, however, it becomes 0 volt AC. So that's why this terminal is drain. In this case, this is source, and in this case, it is gate. Accordingly, you can call this one as common drain amplifier, this one common source amplifier, and this one as common gate amplifier. Right? So 4 possibilities are there. Right? So this is how you can make the circuit. So let's assume that you are in common source amplifier who has given the resistive load. As I told you, you can solve this using some mathematical thing also. So mathematical things, if you follow that, it's nothing but the, what is V out? What is V out? VDD minus ID RD, right? You know what is ID? You keep the value of ID and make del V out by del V in. That's going to give you the gain. So this is the way you can follow that. Take the del V out by del V in. That's the small signal gain. Right. So VDD will go to 0. By the way, this is DC quantity. So minus RD times, when you are going to differentiate it, you will see that this is GM. Right. When you differentiate it, it will become Gm. Right? So you can call this one minus Gm times Rd. Right? So this is, that technique I just kept it for, which is given in book, and book is solving all the amplifiers like this. I assume that you studied this in your previous course, so we'll go with this technique and trick. If it is required, we will revisit that whenever it's required. So as I told you, if input is available here, and if you're looking from this side, what input you are seeing, the impedance wise, what is the impedance looking from source? 1 by Gm in shunt with RO, you can approximate to 1 by Gm. Now, just forget about this part. This part is not there. Okay. Before you making any decision, if you're looking drain side, which is actually output, what are you going to see? What is the impedance? Looking into the drain, R. Okay. Now, when you are going up, forget about the lower part, forget about this, and look at upside, Rd. Note that whenever there is such branch is there, right, there are two branches, then it's in parallel. So effectively at V out terminal, I am going to see Rd in shunt with R0. Note that when you are doing this, at that time it becomes ground, VDD becomes ground. If you want to see a small signal model, some so this is the small signal model. Right. So this is simplest way. So you can see here this R0 and Rd are coming into parallel. Right. So the gain becomes minus Gm times R0 in shunt with Rd. Right. Depending on what value of Rd you are giving, accordingly you can make the decision. Sometimes R0 is much higher than Rd, then you have to, still your gain is Gm times Ro. Right? Sorry, if it is much lower than Rd, then Gm times Ro. If Rd is lower than R0, then it's minus Gm times Rt. So it's depending on what value of resistance you are keeping here. So always people are keeping Rd comparable to R0, so that the impact of Rd will be there. Otherwise, there is no impact. Right? If Rd is very small, then it's minus Gm Rd. Right? You can't keep it in ohms, right? You will also choose something where gain is Rd is actually little bit bigger, right? Here, how to increase the gain? Understand? If this is the formula, how to increase the gain? Because this is what we want to do, right? And right now we are not talking about frequency, so how to increase bandwidth? That's the question of other chapter. How to increase the gain? We have following options: increase Gm, very high. Increase, if you are increasing R0, then what will happen? Then it's depending Rd on. So it depends. First of all, you need to find out which one you want to see here, R0 or Rd, right? So accordingly, you choose the things over here, and wisely, if you do not want to do all these things, you can increase Gm. Just increasing Gm will help you to gain. Or, so how to increase Gm? Let's go this way. If this is same circuit, I am going to give you to simulate it, and I am asking you to have certain gain. So I know that already if I am keeping the minimum WL, the intrinsic gain is around, let's say, 20 volt per volt, which is 26 dB is possible to achieve with this common source. But if I am asking you to make it 32 dB, which is actually double, it makes 40 volt per volt. How to do that? Or increasing to 30 dB, 32 dB. Right? How to do that? How you can increase the gain? So the common answer is for entire analog course, there is only one thing you need to touch, right? W and L. It's very simple. But only thing is which W by L you have to choose, or whether you have to touch W or not, or whether you have to touch L or not. So how to increase GM? Let's say by increasing W. If you are increasing W, of course this will happen, right? So, but I would say if you are doing this, it will also increase capacitances. When you are doing this, it will have lots of problems. But yeah, this first move is good. Now after some times, you will see that GM is getting saturated. You can't go further, right? So then how to increase furthermore? You are more greedy, let's say. How to increase, more gain? Then you have to go to the other side, right? So what you can do? You have to increase. I know that R0 is 1 kilo ohm. If I keep this one also 1 kilo ohm, and GM is in, let's say, 100 ohm, so accordingly, like, I can get the gain of 10 only, right? Not more, sorry, even less than 10, 5. How to get the effective gain in increasing mode? If these numbers, like effective number coming from here, is going in, let's say, 20 kilo ohm, 30 kilo ohm, right? And so on and so forth. Right? If you do that, then you will have better gain, right? So if I want to increase this, what I am going to do? If I want to increase R0, how to increase R0? Let's go this way. Then understand, L you have to increase, but note that in our course we can touch L. Other places like digital, they do not touch L at all. Okay, so if you are studying other course like digital MOS LSI, do not touch L anywhere. L has to be the smallest one to achieve the highest bandwidth. As you are increasing L, it is decreasing the bandwidth. Okay, you might have achieved gigahertz, but because of L, bandwidth will reduce to maybe in megahertz, right? So you have to choose these things very wisely. Do not go randomly. This is what I would say. But this is the way to do it. Maybe with time, when you are going to design some amplifier, you will learn it, that what to touch and what not to touch. Okay, so there is no problem. Here also including the channel, the effect of channel length. Now include the body effect also. With channel length modulation, I have seen the gain of minus GM times R0 in shunt with RD. So what is going to happen when there is a body effect also? Means body is not connected to ground. It is connected to some different voltage, VB. So you just add that. What are you going to see? You can draw the small signal model. Maybe easier one, I can make it for you. GM VGS, and here GM VBS, body to source, sorry, GM BS VBS, then R0, and of course RD will also be here. So looking from here, this side, what are you going to see? 1 by GM in shunt with 1 by GMBS, right? So what are you going to see? 1 by GM plus GMBS. If you solve it, right? So the gain will be, in this case, I know already that output impedance is nothing but R0 in shunt with RD divided by 1 by GM plus GMBS. So that will go upside, GM plus GMBS. But note that still the direction wise it stays minus. Okay, so in common source amplifier the gain will be always minus. Okay, so phase difference between input and output is 180-degree phase shift. Okay, so between input to output there is 180-degree phase shift. Right. Okay. Anything else which is left? Okay. Any doubt in this? It's very simple, right? You can solve same thing with equations also, right? So all those equations are given in Beza result. I would recommend you follow that, and then you follow this also, because this will be very much useful when we are going to build more and more transistors, more and more stages, so you can have the answer. Okay. Now let's keep, instead of resistance, let's keep this one as load. Note that you can identify this one as a diode, because there is only PN junction. One PN junction is there, which is over here, like this, right? Other thing is actually shorted, so only one diode is there. So if you want to realize a diode, then we are going to do this, right? So if you are going to do this, then what's going to happen? What will be the gain? Let's write it down. Gain in the presence of, okay, without channel length modulation. Without channel length modulation. What is the gain? Minus GM1. Let them answer. You have already studied even higher course, right? Minus GM1 by GM2. Okay. So this is the answer for this one, right? With channel length modulation, what is the answer? R not 1. Actual answer is even not R not 1. You can also add R not 2 also. Okay. Of course, it's effectively it's again GM1 divided by GM2 only. Okay. But this is the exact answer without any approximation. Now with body effect. So body effect you can one by one choose for M1 also and M2 also, whichever you like. So let's assume that body effect is there for M1. So then the answer is simpler. Divided by GM2. If here also body effect, then you can keep here. Right? And other things also if you want to approximate. So this is approximated answer. Right? No problem. Okay. Any doubt in this? This is very simple, right? What's your name? I forgot.
Ajay.
Okay. No problem, right? So let's go into. So I change. Okay, this is the correct same only. Now let's assume that this is as a current source. You know that this configuration where gate is connected to actually DC bias, or source is connected to AC ground. Then this configuration generally makes the current as a load, right? So this is current. So now tell me the gain without channel and modulation. So looking from this side, I am going to see 1 by GM1. Looking from here, I am going to see RO1. Looking upside, what is RO2, right? So then the gain is minus GM1 times RO1 in shunt with RO2. Do you agree with this one? Right? It's again an approximated value, right? Now we can add, channel this body effect also, and you can find out body effect wise you should keep. Right? It's quite easy. So now, and you know all these question which I am going to ask you. That there are 3 configuration I found out. One with the resistance, one with the, so with that has a gain of GM times RD. I'm not keeping RO, okay, just for keeping the thing simpler. With diode, which is making minus GM1 divided by GM2, and another was current as a load. So in that case, I have seen minus GM1 in shunt multiplied by RO1 in shunt with RO2. So which configuration are you going to choose and why for having the highest gain? Answer might be like third one or maybe first one also, depending on RD, because it's in your control. You can keep the bigger RD, right? So what about this one? diode connected.
Into 1 by Q2 will be like 10 ohms.
So
It multiply, when you multiply it becomes less than the.
So the important thing which we have to understand over here is three amplifiers are different. Three amplifiers are there. All three are different amplifiers. If I'm looking into this, whose impedance wise, so looking into this, it's infinity. Looking over here, it's RD in shunt with RO1. So if it is winner is RD and RD is very high number, let's say above kilo ohm only, then if it is also high, you can call this one as voltage controlled current source, right? In this case, same is true for this one also, because looking into this, it's infinity. Looking this side is RO1, RO2, both are in kilo ohms. So I'm saying even RO1 in shunt with RO2 are also going to make high impedance. So this is also voltage controlled current source. However, if you're looking into this, this is not making voltage control current source. What is this? What is the input impedance is infinity. What about this one? Output impedance. Output impedance has to be measured at the output. So this is 1 by GM2 and this side is RO1. So RO1 in shunt with 1 by GM2 is winner is 1 by GM2, which is low in nature. So this becomes voltage controlled voltage source. So if you want to have some voltage at the output, then you are going to use this configuration, right? Any doubt in this now? Okay, so maybe other amplifier we will start it tomorrow. Tomorrow is the lecture, or Thursday is there? Thursday. Okay. ठीक है.